This video is to show you how to work mastery level problems in the AC node equations tutorial in Circuit Tutor. There are actually two different types of problems at the mastery level. You would not be allowed to select them, but you would be required to work one of each. So I'm going to do one example of each just to show you everything for completeness. Now, I can, of course, view examples that are fully worked as well, but in the interest of time here, I'm just going to do the exercise. So as always, the first step is to place our ground or reference node, and it's always a good idea to put that connected to a voltage source to minimize the number of supernodes we need to use. So I'm going to just place it here, since that also has a lot of connections. It has 3 connections as opposed to this one would only have 2. Okay, so now I'm going to first do voltage constraints equations. Since we have 2 voltage sources, each of those will produce a constraint equation. And those are very simple equations, so it's good to do those first. So for V2S, I see that it's constraining V6 with respect to V4. And so that'll be a difference of node voltages, and that's going to simply be equal to the value of that source, which is V2S. And that would be 1 angle minus 110 degrees. And the voltage would be, the positive side is V6, the negative side is V4. So this is going to be V6 minus V4 is equal to that. And that is correct. Now, for V1S, I see that that constrains V3 relative to ground, or the reference node, for the reference node that I've chosen. So that'll simply be 1 voltage is equal to the value of that voltage source, and that voltage will be V3, which is on the positive side of V1S. Otherwise, I'd have to put a minus sign someplace for that. So I have V3 is equal to the value of V1S, which I see is just 3 angle 0 degrees. Again, that's the, of course, polar form of a complex number that we're entering there. Now, let's do, since this has a dependent source, it's actually a current-controlled current source. In other words, it's a current source whose value depends on the value of a current elsewhere in the circuit, namely this IX current up here going up through the inductor. So let's do the control variable for that dependent source, because that's something we need to do anytime that a dependent source is present. So we'll enter a control variable equation, and in this case our control variable is Ix, so that's what we have to write the equation for. So Ix will be equal to, and now it's the current through an inductor, so that will simply be a difference of node voltages, since it's not connected to ground on either end, divided by the impedance of the inductor. So now the alpha means I'm going to put in an alphabetic, or a letter basically, alphabetic character, so that will be Ix. And I see that that's going to be V3 minus V6 based on the polarity of Ix, because it's flowing from node 3 to node 6. At least its reference direction goes in that direction. Of course, we don't know which way the current is actually flowing there, and in fact, AC currents actually oscillate back and forth anyway, but we just write V3 minus Vx because that's the direction in which it's pointing, and then that'll be divided by J5. Or 5J, it doesn't matter. Okay, and then we've done the control variable equation. Let's do the SOT variable equation for the current I0, which is the current through a voltage source. Now that can be a little bit tricky in nodal analysis, because the current through a voltage source is whatever it needs to be. And so from the source itself, we have no way to determine what that is. But what we can do is we can use Kirchhoff's current law. Remember that everything in nodal analysis is based on Kirchhoff's current law. So if you're ever at a point in nodal analysis where you don't know what to do, the answer is nearly always use KCl. So that's what we're going to do here. So first I'm going to select SOT branch current, and our current is I0, so that will be equal to, and now I'm going to basically say, well, this current that goes this way is equal to, plus this current is equal to I0. So the current in equals the current out. And these 2 currents go out, so I'm going to sum those 2 currents. So that would be something that's connected to ground. So it would involve 1 node voltage, namely V5. And then this one is also connected to ground, of course, because this is the reference node. And remember that the ground is just a symbol to indicate that this is the reference node. There's no actual current flowing through here, because there's no other ground symbols in this circuit. If there was another ground symbol as well, then we could have current flowing from one of those symbols to the other symbol, as you often have in electronic circuit diagrams. But in Circuit Tutor, we only have one ground symbol, so that's not going to be the case. Okay, so this will be another term like that. So to get the current going this way, that will be 0 minus V1, or in other words, negative V1 divided by the 5 ohms. And then to get the current going this way, that will be minus V5 this time, because the other end here is on V5, so it's 0 minus V5 divided by negative J5. Now, if you wanted to, you could say, well, that minus sign cancels this one, and indeed it does. So we could change that to a plus, and also change this one to a plus. Not really necessary to do that, and I'm not sure there's much point in doing it, but I'll just show you that it will be accepted anyway. Okay, now we need to write KCl equations, which are the most complex equations usually in nodal analysis. So I'll select that, and I need to start with probably node 1. Remember, we do not do this for the reference node because that would be redundant to all the other equations. And here we have one element that is connected between two nodes, and then we have this current control current source, and then an element connected to ground. So I'm going to need a term like this, and a term like this, and this is the term for the current controlled current source, as you can see there in the little hint, and that's equal to 0. And so for node 1, the J5, that's going to be V1 minus V5 divided by the J5 ohm impedance. And then the current going to ground through the 5 ohm resistor would just be V1 minus 0, or in other words, just V1 divided by the 5 ohms. And finally, we need to add the current leaving node 1 to node 2 through the 5ix current source. And of course, that's just the value of that current source, since the arrow does point in the direction that we're trying to add, which is the current leaving that node. So there's no minus sign required there. So this will just be 5 times ix. Remember, the little alpha symbol indicates that you're going to put a letter in there. And that is correct. And now we'll write a KCl equation for node 2. So now we have this term entering, so we'll have one of those, and then we have two impedances that are connected between nodes, so we'll have two terms like this, and that's all going to be equal to 0 by KCl. So let's add the current going this way. Now that's the negative of 5x. So we have minus 5ix, and then we have the current going this way through the J8 ohm inductor, so that's going to be V2 minus V3 divided by J8. And then we have the current going this way, so that's going to be V2 minus V4 divided by now minus J2 ohms. And that's it for that equation, so that's correct. Then we need to write a well, we need to look at node 3, and we say, okay, node 3, we have a voltage source connected to that node, and remember that the current through a voltage source is whatever it needs to be, which means we don't know what it is. Now, we did actually write an equation for it before, but right now, we don't need to write an equation for that, because we already have a constraint equation for that voltage source, and it's basically part of the reference supernode, so we don't write a KCl equation for node 3. Instead, we'll go to node 4 and write a KCl equation there, but again, we have a voltage source connected to it. So in that case, we don't know the current through the V2S source, but we can now form a supernode consisting of nodes 4 and 6. So we're going to draw a KCl surface around those two nodes, including the voltage source, and then we won't need to know the current through that voltage source because it's going to be internal to the node, and it's not going to be a current, or I shouldn't say internal to the node, but internal to the supernode. So it's not going to be a current that exits that closed surface, which we call a supernode. So we have one current exiting here, which will require that type of term, and then another one exiting here, which requires another term like that, and that's going to be equal to 0. So we can write that as V4 minus V2 divided by minus J2 ohms. That's the current exiting down through the capacitor here, leaving node 4 that way. And then this current leaving node 6 through the inductor will be V6 minus V3, because those are the voltages on either side of the inductor divided by the inductive impedance of J5 ohms. And again, all the nodes that are part of the supernode are going to have positive coefficients. So node 4 and node 6 have positive coefficients. All the other nodes in this equation will have negative coefficients, since I'm adding terms that leave that node. So that is correct. And let's see, so we've done that. Now we also need to do one for node 5. We've done nodes 4 and 6, but we haven't done node 5 yet. So that will require one term that's going through an impedance to ground, and then another one going to a different node, so that would be like that. And that will all be equal to 0. And so the one going to ground would be V5 minus 0 divided by negative J5 ohms, the capacitive impedance there. And then, so that's the current going this way out of J5, and the current going this way out of J5 would be V5 minus V1 divided by the J5 ohm impedance. And if I'm not mistaken now, that should be all of the equations that are required. So we just click no more equations. And indeed, we're finished. Now, I'm going to skip the detailed explanation here and just work a problem of the other type on this level, just to be complete. So this problem will be a little bit different, and again, we need to place the ground. Here we have two voltage sources connected to this node, so that would be a great one to place my ground. So I'm going to place it there. And once again, now I have actually 3 voltage sources, so that will require 1, 2, 3 voltage constraint equations, because each voltage source requires a voltage constraint equation, whether it's independent or dependent, as in this case. So I'll select that, and it's good to start with those simple equations. So let's do V1S first. So that's going to constrain node 7 voltage with respect to ground. So we'll just have this type of term, and then equal to the value of that source. So basically, that's going to be the plus side, which is 0, minus V7. So we're going to have negative V7 is going to be equal to the value of that source, which is V1S, which I see here is 7 angle 0. Now, I could put the negative sign on the other side instead. That would be fine. Or I could change this to a plus and make this 7 angle 180 degrees, because 1 angle 180 degrees is the polar form of negative 1. But I'll just leave it like this for now. Now let's do it for the V2S, and that's the difference between V2 and V1. So that would be a difference of node voltages. And so that would be the plus side, which is V2, minus the minus side, which is V1. And that will be equal to the value of V2S, which is just 4 angle minus 90 degrees. And finally, we have the dependent voltage source. This is a current-controlled voltage source because it's the value of the voltage is some what we call a transimpedance in ohms multiplying the value of this current Ix, which is this current actually over through this capacitor in a different part of the circuit. And that determines the actual voltage across this. So here, this voltage source is connected to ground on its minus side. So we will need basically a V5 will be equal to a value like that, which is the value of that voltage source. So we put in V5 there because that's the positive side of this source. And then the value will simply be the 6 ohms times Ix. Now we don't make any substitutions at this point. We just put it in as written on the diagram. So that is correct. We're done with our voltage constraint equations. So now let's do the control variable for the dependent source. So the control variable, remember, is the Ix value. That determines the output value of this source. So we need to write an equation for Ix, which we find over here. And that's basically going to be given by an Ohm's law type of equation. So we'll need a difference of node voltages. Or I'm sorry, I'm writing the wrong type of equation there. So we need to, this is going to be the control variable equation. I forgot to select that. So this is going to be Ix equals the difference of node voltages divided by the impedance. So we fill in that as Ix. And then that's going to be the high voltage, the V6, minus the low voltage, V4, divided by the capacitive impedance of negative J2 ohms. Okay, that's the control variable equation. Now, the SOT variable equation is a SOT voltage V0, which in this case, again, appears across a current source. But actually, this one is rather easy. Unlike the current through a voltage source in nodal analysis, this is actually quite easy. So we just write that V0 is going to be just the difference of two node voltages. So we put in there V0. Oh, and I'm sorry, I actually picked the wrong type of equation here. So this is a control variable equation. I forgot to change it to SOT branch voltage. It'll be similar, but we have to use this type, and it's already pre-printed for us. So V0 is equal to just going to be V5 minus V7. V5 is the node voltage on the positive side, and then V7 is the voltage on the negative side. So that is the SOT branch voltage. That's the correct type of equation we're entering here. So that takes care of our one SOT variable. Then we have to write a KCl equation for each non-reference node or supernode as is applicable. So let's do KCl equations. We'll select that. And let's just go in order here. So the reference node, of course, we don't use. So let's look at V1. Well, V1 is connected to a voltage source. And remember, the current through a voltage source is whatever it needs to be. So we have to form a supernode consisting of nodes 1 and 2. So we're going to draw our KCl surface around both of those nodes and then add all the currents that exit that larger surface called a supernode. And you see there's going to be one current going here, and a current going here, and a current going here. So they will all be differences of node voltage. So we're going to have three such terms divided by impedances. And so the first one would be V1 minus V4 divided by the 6 ohms. That's just Ohm's law for this current going here. And then the current going up through the inductor would be V2 minus V5, high to low, divided by the J1, the inductive impedance. And then this current would be just V2 minus V3, again high to low, divided by the capacitive impedance of negative J5 ohms. Check that, and that is correct. And that takes care of V1 and V2. Now let's do V3. So now we don't have a voltage source, but we have one element going to ground. So that'll be this type of term. And then one that's not going to ground, which will be that, equals 0. So we're going to have V3 here minus 0 divided by J3 ohms. And then that's the current through the inductor. And then the current here will be V3 minus V2 divided by negative J5 ohms. And that's node 3. Now let's look at node 4. And we have two elements there that are not connected to ground. So we need two terms like that for node 4. And so we're going to have V4 minus V1 divided by the 6 ohms. That's the current down through the 6 ohm resistor. And then we'll have V4 minus V6 divided by negative J2 ohms would be the current going up through the capacitor. Those are the two currents that leave node 4. So that is correct. Now we'll look at node 5 and say, okay, node 5 is actually connected to a voltage source. Doesn't matter whether it's independent or dependent, it's still a voltage source. It still has those little plus and minus signs in there that tell us it's a voltage source. And it is connected to the reference node. That means it's part of what we might call the reference supernode. So we do not need to write a KCl equation for node 5. And we will not attempt to do so because you really can't. So let's go instead to node 6, which has two impedances connected. So neither one of which goes to ground. So we need two terms like this equal to 0. And the first equation will be V6 minus V4 divided by negative J2 ohms. And the next one will be V6 minus V7 divided by J4 ohms. That's the current going to the right through this inductor. Okay, so that takes care of node 6 and node 7. Again, that's actually part of the reference supernode again because it's connected via voltage source to ground. So we don't have to do anything for that. So basically all of this here, all of that is basically what we call the reference supernode, and we don't need to write an equation for that. So we don't write anything for node 7, which means basically we're done. And if we weren't sure about what we did, we could view a more detailed explanation, which I'll skip now in the interest of time. Thank you.